Hey everybody. Let's see, am I sharing my screen appropriately? Okay, cool. Hey guys, I'm gonna be walking us through today um, the first half of the RealityNet library slash SDK, whatever um, demos and walkthroughs, and this one is going to be on deploying your infrastructure and actually implementing your nodes and consensus. The second half is going to be on actually like hosting and deploying your Turing-complete applications in the reality interpreter and the thing that runs them, but also generates reality checks. And as well as how to like join your rApp to the test net. That's going to be the second half. This first one is basically like how do you create sort of like the actual infrastructure that becomes your rApp network and sort of how to actually like test this stuff, launch like a cluster and do that before you actually do your main net. So the first thing here, I'm using Scala. You can use other JVM languages. I mean, like technically they say any other, but like you're probably better off using Scala, Java, or Kotlin with the interop. Probably wouldn't try this with Clojure, but basically what you want to do is use this interface called Portal. And Portal is basically it imports and creates a bunch of just kind of like reusable infrastructure kind of scaffolding code necessary in order to like launch and create your consensus processes. You can sort of think about this almost like this whole thing right here, Portal, is basically just one big fancy like HTTP server. And what we're going to do is define actual like consensus processes or like, blockchains themselves in terms of like one chunk that is a consensus process, and that's called a CoCell. And what we do is we instantiate these CoCells, and then we define them, the CoCells, and then instantiate them, like create instances of them here in the portal. And then Portal basically runs them. Portal itself is similarly kind of like an interpreter as well. There's so many different interpreters, but you know, basically what's going on here is that we are taking instances of certain algorithms and then sort of enqueuing them inside of a server that basically runs them and sort of incubates them on the back end, and not on the back end, but just sort of like yeah, totally independently and in parallel. Okay, so first things first is we're going to talk about the something called a CoCell. So I'm going to create this thing called a case class. So it's going to call walkthrough. I'm going to call this walkthrough L0. And what we want to do is extend CoCell. CoCell is really cool. It's very special in the fact that what CoCell does is it basically defines the interface, rather the context around which something called a cell, namely, sort of like to go to a co-cell. A cell is actually like the implementation of a consensus process. And so what this does is it's sort of a way of actually like packaging around, I guess you could call it like an environment, or not an environment, but basically it's a context is the right word. It's basically like a thing that that sort of sits next to, I guess in our context, like a monad, or just some type of like a like functorial operator. And what it does is it sort of ferries information back and forth. This is similar to other things in functional programming. I should not Google this right now, but you can Google it. I'm pretty sure it's like a what Claisley or something. Please forgive me if I forget which one it is, but there are many like this. There's similar, concepts in like Spark, Apache Spark, um, and whatever John DeGoe's library is as well. I don't know if they necessarily use Common as we can sort of blend them, but bottom line here is that what this does is it basically creates like a sort of universe within which your consensus process can live, and you define shit that you parameterize your consensus process with. Okay, so like every single different consensus process is something called a cell. Like I said before, and in order to actually define your co-cell, what you need to do is create a method called makeCell. I did predefined this stuff before, so I'm just going to sit here typing, but sort of walk through like, what we're doing here. And so this make cell method, what it does is it's basically like a class factory. And what it does is it returns a function mapping the universal object omega, alpha and omega, whatever. It's actually also a thing from like category theory or type theory, maybe even chain complexes or dynamical systems. I don't know, but I think so. I think all three. But they call sort of like the terminal object omega. And what we do is we create this instance of a cell, or it's basically like this right here is a function. So it's a function returning a function, which there's a lot of fancy ways of doing things in Scala. It's kind of like a class factory-ish. Some CS nerd can hate on me. Feel free. But yeah, it's a method that creates instances of your class. And so basically, you have this thing called an L0 cell, right? It itself has its own like make cell method, at least if we want to define things in terms of like the cell zero process. Basically, like we're just using an object where like this concept lives, but like when you're actually building your own shit, you can put, this make cell method for the L0 cell, like anywhere. You don't even need to necessarily like split them up. I'm just not copy and pasting this thing from the internals to make it more, clean. But basically, inside of here in this make cell method, it's a hylomorphism, a type of recursion scheme that is parameterized by two things, a like anamorphism and a catamorphism, which are analogous to a algebra and coalgebra, or build up and tear down structures. Coalgebras build up a structure, basically take an input, create a like computation space, a monad where like computation is done inside of a black box, and the algebra basically tears down the black box, gets rid of all this shit that happened, access data, all that stuff in the background, and then returns a result. And is able to do this by, it also gives us the ability to know that there's like specific types inside of the state transitions of this kind of process. So they're kind of like a typed state machine. We do use a state machine under the hood actually for the L0 process, which is really important for anybody who wants to like build stuff with reality, because L0 is basically how you connect to the wider network itself. So this L0 process is sort of like the kind of like programmatic gateway to RealityNet. Your L1 is really just sort of like your domain specific. I mean, you can put your own custom shader here in the L0 as well, but like the L1 is like where you build your own rApp cluster and shit. You can also like, you can make your own, you can use our framework, you can use a, external L1 like Bitcoin or Ethereum as a base or something, but regardless of what you use, you connect it to the L1. And so what happens here in the L, or sorry, this is the L0. So the L1, whatever you use, it connects to the L0. And then there's two sort of like, state transitions that happen here. We have L1 information here. In this case, since this is like actually like a pre-built implementation of an L0, it uses the net L1 because that's what's part of this example. But if you wanted, you could basically make this like ETH blocks, or you could make like your own kind of block type or something. You actually don't need an L1. You can just use this L0 process and sort of like use your rApp as like a way to span data or create some kind of like, just some kind of record of some shit on our network. I mean, you're gonna have to basically like, I'll skip it, but basically you're not gonna have as great a security guarantee as if you used an L1, but it could be a lot simpler for individuals who might be just interested in like swapping tokens or something like that. If you guys just wanted to use a centralized backend or something, you could probably just yeah, regardless, there's this case which processes these L1 blocks, and then another one which actually kicks off the consensus process in an L0 called a state channel, sorry, a snapshot. And so basically a snapshot is the equivalent, it's like the L0's block. It's basically the partial order inside a topologically sorted graph of particular like ranks, I guess you could say, going from zero or like the terminal object into infinity. This is like a collection of all the different blocks that are proposed at a certain height. A Bitcoin equivalent would be like blocks in Bitcoin that are sort of like neighbors or like cousins, I think is the word, relative to a parent uncle. We would want to keep all that information around in our L0, because what we do is we create something called a finality proof, which allows us to actually like guarantee we have the correct total chain state, and we're selecting the like most correct or like valid fork basically in the case of a ghost chain attack, which is really cool. And so it's kind of heady and esoteric, and we're not going to get into that algorithm per se today, but that's what the L0 does. It's basically like every time if you are an L1 out there and you want to be able to integrate with all the other L1s that are connected on Reality, you basically run an L0 process next to your L1 process, and you just interact with the L0 process, and it allows you to find every single node running every single like protocol out there on every single server. And you can do some really cool stuff with these finality guarantees we have, like swapping without liquidity pools, which is really cool, and amongst other things. That's what net is. The star token's part of yeah, people use it. And okay, so this is the L1 process. We basically talked about, creating this consensus thing. There's one other cool thing. I'm gonna actually we'll talk about this later. So the next thing I want to talk about here is actually creating your own. Oh yeah, we need to basically, in general, um, if you're just using a stock implementation, you can just reuse the actual definition of how to do a startup. But if you want to basically do something and configure it yourself, like open up some ports and do things with like adding extra endpoints, things like that. If you need to add, change certain ports and whatnot, you basically change all the stuff inside of the startup method. It's pretty self-explanatory. Go in here and figure out how to like pull these different command line arguments out. But basically all the different like subcomponents of the actual class that get created, they just read in from this configuration, and they use it to basically pass to you know, the startup methods. Pretty self-explanatory. Okay, cool. So moving forward, we have, God, ugh, man, my back is fucked. Okay, basically, moving forward, we have this, we want to create our own L1, basically, right? We want to do something a little bit more cool, more cute. And so basically what we're going to do is create an L1 process. So, you can use our stock implementation and add shit onto it. You can also like, run like a specific L1 node next to this jar that gets created. We'll show you how to do it later. And sort of talk to each other over like sockets or just like ports on the machine. You could also just like create or like load up an instance, like theoretically, at least of like, like, I don't know, something written in Java, like ETH4j or Bitcoin 4j, and have this actual node instance inside of the same JVM, which would kind of be cooler for security guarantees and stuff. But it wouldn't really be, I don't know, it'd be really hot. Regardless, there's a lot of different decisions why we would do what we would do. But you can basically make your own sandwich with these L1s. Right now, we're just going to take the stock implementation of RealityNet L1, and I'm going to show you how that works and how you can configure it and extend it in order to create your own L1, rather than like basically writing everything from scratch. You can basically take something that works and add to it or subtract to things that you don't need. So you have case class again. This is our walkthrough L1. Okay. Actually did not write these case classes, so we have the air of some live hacker coder shit, yo. Okay, cool. So here I have like just the previous implementation of the make cell method here with the L1, and just gonna go just actually define this thing right now. We'll be coming back to talk after I do the deployment to show you a little bit more about how you can just sort of in a clean way extend some of these sorry, you can actually basically like combine the logic inside of a cell, which is pretty cool, and we'll do that later. So this L1 process, the thing you pass in here as opposed to the L1 output queue and the state channel output queue, um, it's basically just sort of you know regardless, we'll talk more about that later. That's the context for the comonad of the CoCell. So the context here is basically like your data access object, or rather, it's the cache, or like basically they're mostly caches, but it's just like the data access object for each specific like consensus project, or sorry, consensus process. There's multiple of these that get created inside of one giant monolithic DAO under the hood. But this is where you just define the scope of what the context is between these different consensus processes. And so this is where your parallelism comes in. You can parallelize these individually, or like you have multiple access across these co-cells. Well, you don't really actually have to do anything. Cats and this multi-threading library under the hood basically handles all that access stuff for you. So yeah, you can think pretty monetically about this stuff. So that's cool. Yeah, thanks for my TED Talk. Anyway, so here's the one for block consensus, CTX. At least if you want to use RL1, very cool. Basically, you're going to take a look at one of these. So you have a bunch of different like caches, basically. Caches, I mean, we could, some, there are some databases around here, but this is mostly in-memory stuff. So transactions, information about consensus, yada, yada. Um, you can change this as well if you want. You just have to change the startup method and create new caches for new information. This is something I can also show you as well inside of the first wrap that was created. Information about ZK proofs from some Turing-complete code running inside of the reality interpreter instance, generating reality checks went into blocks, and it was pretty cool. So just moving a bit further on, what does this want? Oh yeah, can't forget. Basically, we need to define the type of functor that's being used for cat's effect, what kind of attributes it has. It's secure. It's random. It's so random. What else is broken? Make resources. Oh, that's interesting. All right, I'm gonna cheat. I'm tired. This is a lot of shit. Regardless, I'm gonna go get that in a second. Is it async? Yeah, we did need a new maker. So sometimes, actually, I'm glad I just popped over here. So sometimes, you need to actually create new stuff, like this make resources thing. And so what make resources does, the fuck that again? Oh, I'm an idiot. Yeah, I needed to talk about this anyway, but there you go. Glad I did that actually. I would have forgotten. Okay, cool. So essentially, these resources right here, like creating new instances on like your L1, basically, or not instances, it basically creates like a new API, new endpoints and shit like that. So basically, like right here, specifically, if you want to actually like create one of these state channel instances, you need to create resources that are necessary, in order to actually create something called an FS2 pipeline. So what's really cool about our L1 is that it's not actually just like a fork of like Bitcoin or Bitcoin Cash. It's literally like a large scale data processing pipeline using like, I mean, it's pretty, not arguable at this point. Like FS2, you can do literally anything, pretty much anything, at least in any major big data library, just like on top of FS2. It's like both the simplest and like, in my opinion, like most powerful thing. You can pretty much, if you've got a streaming library, you can do batch map reduce or anything like that. Um, so I'm just like, might as well have a giant Swiss Army knife. So we're gonna pop over here and take a look. So this actual cell creation process creates a special type of a block called well, it creates the node inside of a directed acyclic graph, and the nodes inside the directed acyclic graph are actual cryptographic blocks. They are triangles formed with three edges between a facilitator and two peers, forming a flat surface, a triangulation or tessellation, if you will. Um, and yeah, same thing as before with your coalgebra. You basically just build up the actual like consensus round, if you will. There's like a multi-stage process here, and actually a diagram that should be inside of the documentation. But it's just a fancy message passage flow that creates this topological data structure. And what's important about it is it has topological order, which gives us some notion of time. It does have parallelism, so things can happen at the same time. But at least like even if two things happen at the same time, it's like we can encode that in a data structure that also has linearity or causality, I guess you could say, inside of that like continuum. Okay, cool. So here we have this like walkthrough L1. Amazing. We've created our resource methods. Fantastic. As before, I'm just adding this override def because, if you want to basically make your own thing, your own kind of like data pipeline, which you'd want to do, and you'd actually need to do is create a new setup method. So right here, the last kind of component here is the FS2 pipeline. So basically, that is this FS2 pipeline. This right here, it's already predefined. We use it called the L1. What you'll do if you want to create your own pipeline is you will create a make method on a class called make state channel. For us in this case, we basically create an instance of a class called L1. So if you want to make your own, state channel pipeline, there's a couple of different ways to do this. Um, the easiest would probably just to be to create this own class, like your own, like extend this class and then add new attributes to it. Or you could also like add together two specific pipelines themselves. That's a bit more complex, but I mean, I would only do that. I mean, you cannot have it working and stuff, but I would do that basically if you just wanted to take two pretty complicated, like well-written pipelines, put them together just inside of the same like node instance. That's what I would do, and you have no real reason to try and introspect this object, this like FS2 pipeline at all, and it's just going to stay like two pipelines connected together. I would just do it that way. Anyway, we're getting into the last thing I'm going to talk about, which is our monoid, and maybe I'll just work backwards here from the L1 to the L0. So first, let's finish off this FS2 pipeline. Um, so what this does, first, it creates the block consensus context. That was that CTX that we saw earlier. And so that's really important. That's basically like all the different data stores and stuff that get accessed throughout this pipeline. You have an instance of your cell like before. This just takes this generically from the constructor. But what's really happening here is that you're opening up a bunch of these different streams and you're piping them through your cell. So we call this a state channel. And a state channel is essentially like a data channel, like what these FS2 pipelines or streams and pipes are. But it's passing through a state monad. State channel. That's what a state channel is. For anybody, anyways, I don't know, but that's a state channel, and basically, there's a couple of different things in here you can just add, like different uh, basically like these little like logical flows where you can pipe shit through in order to make state updates. For us, this all just implements consensus, but like in the next example, the last one, I'm going to show you the first wrap that was created. It basically it picks up information on ZK proofs and also client applications from video games and stuff and passes this through here, puts it in blocks and does a lot of fancy stuff with it, all the while making sure everything is immutable and cryptographically secure. So I'm just scrolling here to find this, the most important thing, which is our runtime. Okay, and so runtime is it is also an interpreter itself, FS2, interpreters and interpreters. But yeah, basically what this does is it just creates long-running programs under the hood that stream information from endpoints through these different sort of like junctions and gaskets, and at each point uses either in its own, functor thing or like a functor we create in order to change or do things. And so these are two things. Block consensus is the main real, runtime, but that just sort of gets mixed with these different like actual, inputs. And then that's your whole, FS2 pipeline. This right here is like this is like streaming MapReduce basically. Um, I mean, you're literally just like mapping and reducing on tuples and whatnot. It's the same thing. So, yeah, it's really cool, man. So if you actually use RealityNet to build your L1, this thing is literally like a large scale data processing cluster. It's not just like running some like old fork thing of Bitcoin. It's a completely new thing, and I think everybody should be using it. The performance really just is kind of unparalleled. But I mean, obviously, like we want to make connections for other different L1s for liquidity, we're going to do that. But um, yeah, I don't know. You pick your poison. All right, so we have that, and then the last thing we do here now that we've defined two different instances, we could have just done this L0, but instead we defined an L1 as well. What we're going to do is we're going to create instances of these actual like co-cells themselves, and then create something called a cell program. So cell program, this is actually the real like main interpreter, I guess you could say, not of like just a streaming DSL under the hood. You can sort of like mix these two things, but this is the one that actually picks up all this different kind of like domain specific logic. Like these co-cells are basically just kind of like a higher level syntax, if you will. And so it picks all of them up and sort of enqueues them into a runtime and then just like, has them do things. And so what we do here, this is actually meant to be basically a method, although it's defined in a very interesting way. And so this gets picked up by, yeah, the main like HTTP, server itself, kicks up all these processes, creates the thing, and yeah, we're off to the races. So it's a list of string, cool, and then yeah, basically do for I'm just gonna find this real quick. CoCells. Okay. Okay, cool. So then we want to sequence this, yield this. Cool. There we go. A thing that does a thing. Okay, right here now we have two instances. I'm just gonna do it this way. Just for clarity, you have this and you have this. Can't forget our instantiators. Gotta have our parens, baby. Here we go. Okay, cool. Now we actually have this thing, which is how you run an object. So the thing that you want to do now is compile your code. Um, it's going to take like a couple of seconds, but I actually have all of this written out, properly in another file, and it's been compiled. And so what you can do now, inside of your, repo like project or whatever, you can use our Docker containers in order to basically like, create a multi-node cluster on just your local machine for testing things. There's a couple of different ways that you can find in our Docker, or sorry, our Discord related to not just Docker, but well, Docker for local specifically, but then also Kubernetes with scaffolding as well in order to launch like large clusters, on like AWS and uh, DigitalOcean is what we've also done that with, and you can also just do them individually as like servers on bare metal, like we do all the time with our testnet, but all that's in the documentation. So yeah, I mean, basically, if you go over here to terminal just inside your thing, like where your project is, right now it's just running the main Reality project, but yeah, basically you just run Docker Compose up. It reads the local jar from your Docker files and it just launches up like a three node cluster. So we're gonna take a look here and see how that works. Um, but yeah, this is yeah, how you can do that. It's fun. So yeah, these Docker files you can if you want to use them in your project, you can just move them over. The last sort of thing I'm going to show you before teeing us up for the next call basically has them in their project. They're using it to do the local test thing. So gotta love it. It's taking a sweet time for a live demo, but we're gonna have some shock. Oh, there we go. Well, I'm not shocked, but I'm awed at how slow it is. Um, I mean, you can take my word for it, but we're already here, and these are long takes, so we're gonna get that proof point, baby. Come on, come on. All right, maybe I'll just switch back. Um, anything? Anyway, we'll switch back. Takes a second, but yeah, I'll show this right at the end. So, last thing, now that we've seen, deploying this actual cluster thing, let's see if maybe it worked. Taking a sweet time. Oh, there we go. There you go. So here you have a three node cluster that's getting started now. And yeah, all these guys are joining each other, and we see this, all the peers know each other, and it's about to kick off a cluster. And you can basically access this directly, either through their endpoints, or if you want, you can like SSH into, or just whatever you do through the UI or SSH or whatever into the Docker containers. But yeah, okay. So last thing, which is really cool and kind of important, is like what else can you do with like your L1 when you use Reality? So yeah, basically. you can do this really cool thing where you can host Turing-complete applications inside of our like interpreter. And what it does is it implicitly outputs ZK proofs for just the execution of this just generic code, anything that can compile the WASM. Um, that's really cool. So I'm going to show you how this works. Just, pre-built interface that we have inside of just the Reality repo. And what this is, it's another instance of L1, but what it does is it creates a instance of this WASM executor, which I've been calling an interpreter. I don't know. I hate that term executor, and it actually does a lot more than just execute like, some kind of binary. Um, so I don't know. Maybe I'll just change the name, but whatever. The what it does is it basically creates an input stream to then send information and into and out of this WASM executor, and it enqueues that up in the runtime of like the same L1 thing. So it sort of sits here. So what you do is that you now inside of your L1, you basically have this interpreter that can like check Turing-complete code inside of your pipeline, and the combination of those ZK proofs plus the state proofs can give us like the concept of a distributed application that can sort of self-introspect on itself, which is kind of like, both a solution. It's like a solution to this thing called remote code verification, but in at least a distributed sense. It's a basically like a solution to the halting problem, in at least this sort of context. So it's very cool, and I'm going to be doing a lot of cool stuff with it. But yeah, I think it's sick. And so, yeah, on the topic of other cool shit, and sort of the next thing we're going to be talking about, which is how do you basically deploy one of these applications into one of these WASM output streams, or not output streams, sorry, the WASM executor right here, and then basically how do you like connect your reality or your RAP, cluster or your RAP network to the wider RealityNet network, and sort of like the equivalent of like in the Ethereum Hello World application, like how do you basically deploy your smart contract? So right now what we did is we created like we've created our own RealityNet, our own RAP network. And so what we're going to do next is we're going to see how to basically put our own applications on a RAP network and sort of treat that RAP network like it's its own, independent cloud computing network. Although it's actually just a blockchain. It's just yeah, the world computer. Okay, so this is the first RAP that's ever been built and put in production. It's called or the company's called Cyberlete. I think the app is too. There's a lot of different stuff they do, but this is their Cyberlete RAP, their cyber app. I don't know. But basically, what we've done here is we've created a new instance, or sorry, yeah, a new instance of a state channel cell object, which is the thing that creates the make method, right? There's this new like ZK-WASM executor, which is a different like it's like a new class that you can wrap your actual main code in. We'll talk more about that next time. But yeah, that's something that talks to the other one, the other executor inside of the sort of the library. And then those two things are now accessible, right, from this make cell method, which is the make cell method for a new L1 process. And this L1 process actually, in addition to executing, or rather running, or rather interpreting all the commands that have come in, which are basically just, like people who will send in input data and then the method on some type of like piece of code that's inside of the WASM interpreter thing. I'm just gonna say executor. I don't know why I keep trying to stop it. We're just gonna execute everything and everyone, baby. So basically, um, yeah, this whole data pipeline also takes the output of these ZK proofs and puts them inside of blocks so that people can access them, which is really cool. And so this is a pretty big, long thing that's actually doing a validation for the specific use case of trying to make sure people aren't cheating on video games that are hosted on this RAP network or these RAP nodes. So it's very cool. There's a link out here for you guys to check it out as well. This is, also the most complex RAP that's ever been built and a great place to start in order to see how to like build your stuff. So yeah, that's pretty much it. Yep. As you can see, these guys, they've also got their own CoCell here. They're using a state channel instance. They're just reusing the same stock L0. Oh, and the last thing I forgot to tell you about, which is, oh yeah, really cool. So we have this cool thing called a monoid, or the ability to add different cells together, kind of just like adding numbers, like 1 plus 1 and 2. What this does is it takes the logic for one consensus cell and another one and sort of adds them together. So here we have the Cyberlete WASM executor state channel like make cell method, and we also just have the basic block cell method, which is used in order to like put stuff into blocks, right? Because we want to make sure that all the stuff that's getting sent into the WASM executor is going to yeah, end up inside of blocks in order to like prove the actual like flow of information through the network in addition to how things were the code was run or whatever. And so states that are transitioned, we can prove that everything happened in the right time. So if we want to move back here, I mean, this is a great time to stop. So in the actual like core like reality repo inside of our little playground, all this you basically, by the way, if you look at the Cyberlete repo, when you create a new project, you just sort of like import the reality project in here. And once it does, you can basically just like access all of the combined directories. It's because it's your own project now, but like you can also do all this within the reality repo. It's just kind of like like a scratch place. So right here inside of our walkthrough example, I have a couple of simple things. I have an instance of a dummy L0 cell that we can add together. Um, and yeah, this is really cool because if you wanted to, for instance, add extra logic um, to the L0 process, what you could do is you could just implement a cell yourself in its own separate like file and not actually have to like modify, and change the core cell instance inside of the reality code base or like extend it or anything, which would be kind of a pain and hard to like see. And so adding these things together is really helpful. So this combined method's basically just like this is the full method call, but you just add it together like a plus. And then for the L1, like we saw with the Cyberlete guys, they basically have yeah, this one that we just took a look at. Whoops. Shoot, shoot. Yeah, yep. And so these two things are added together using the combine. So yeah, that's really just the basics of how you modify and create your own network. There's a couple of different attributes also you can add as well. Especially creating your own endpoints and things like that. Really briefly, I'll touch on this, but it's probably better just to look at the core examples. I might make another video if somebody asks for it or something, but yeah, I mean, if you take a look at like right here, we have this thing called you have like a make resources method and stuff. You can basically use that in order to pass stuff into CoCell. But yeah, I mean, basically, like if you want to create a new instance, let's say of like, one of the different APIs and add some endpoints to it, like for instance, the L1 API or something, you would just create a new class that, creates a new, make resources, and then basically it adds these endpoints directly. So it's kind of the last thing. I'll add some more color to that as people ask for it, but there's a pretty good example already in the docs. So, all right. I think that's it. I'm no longer sharing my screen. That's the first half, and we'll be sharing that and getting everybody to start running their app clusters. So yeah, if you're seeing this video, you should definitely know where to find us, and we look forward to seeing you in Discord and Telegram. Thank you all.